A very good morning to one and all present here. I'm glad to welcome you all to the second day of the fourth induction program for research scholars. I welcome the online participants also. Today, the first session is on Statistical Inferences by Dr. A. Pir Mohamed Sir, Professor of Eminence, Department of Textile Technology, AC Tech, Anna University. We are happy to have you with us, Professor. I now invite our Director Madam, Dr. C. Umarani Ma'am, to felicitate our guest with a bouquet and a book. Kindly accept it, sir, as a token of our love and appreciation. Call upon Dr. Kumaresan, sir, our Additional Director, to felicitate sir with the book. Thank you, sir. Thank you, ma'am. Let us have a brief introduction about the speaker for today's session. Professor Pir Mohamed Sir did his bachelor's in textile technology from PSG College of Technology, Coimbatore in 1980, and he obtained his master's in textile technology from Indian Institute of Technology, Delhi in 1983. He earned his PhD degree from Anna University in the year 1992 for his notable research work on yarn spinning. He joined Anna University as a teaching research associate in the year 1986 and rendered his services to this university in various capacities. He was a professor and now a professor of eminence in the Department of Textile Technology, AC Tech Campus, Anna University. To mention a few of his commendable services to the university are Director, Center for Affiliation of Institutions, Director, Center for Faculty Development, and served as Director for Planning and Development. Professor is former Vice Chancellor of BS Abdur Rahman Crescent Institute of Science and Technology. He specialized in yarn engineering, statistical applications in textile engineering, mechanics of textile structures. He holds several research applauds, which includes funded projects, publication in reputed international journals, and also granted patents. We are glad to have you with us, sir. Over to you, sir. Thank you.
Good morning, all of you. Director, Center for Research, Deputy Directors, and the officers of Center for Research, and the research scholars. It gives me immense pleasure to participate in the induction program organized by the Center for Research for the benefit of the research scholars. Anna University is unique, in particular the Center for Research is unique in organizing the induction program. It's not necessary, it's not incumbent upon them to organize such program, but they take it as a matter of responsibility to update the research scholar. Whatever happens in the field of their research, so that the research outcome would be good and beneficial to the society. In one of my previous lectures, I stressed upon that whatever the research we do is not for the purpose of earning a degree. Final outcomes should be beneficial to the society. That's the most important thing. You should, all of us should keep it in your mind. And the benefit could be in terms of a new product, or in terms of a new process, or at least contribution to the field of knowledge towards understanding whatever the phenomena the people are concerned. So improving upon the knowledge itself is a contribution from the research work. And when I was interacting with the director, I came to know that you are also given exposure to the latest technology like artificial intelligence and IoT. So I have a long experience, particularly in our university, Anna University. I also have a short stint of experience with a private university. My interaction with different level student, faculty, and higher officials and other scientists, I come to know that I realize that the application of AI, machine learning, and IoT is essential. It's not optional one. It is essential. Without applying these new technologies, you cannot come out with anything new. You cannot innovate, you cannot discover. So we will be doing the same thing, maybe in a different form. That may not be useful. As I said, that it should be useful to the society. So whatever field you are, whether arts, science or engineering or technology, you keep learning. It's not a one-time affair, definitely. You should keep learning these new technologies and connect with your field, and definitely you will come out with new innovation, and you can patent it, you can commercialize it. It's all possible. So this is the idea I wanted to share with you, because all of you are research scholars. The role of research scholars is very, very important. Now it is realized very much, actually. When we were studying, actually getting a UG degree itself is a great thing, and going for a master's degree, and somebody may prefer a PhD. Now the government, whether the central government or the state government, giving a lot of priority for innovation. Innovation cannot come just like that. And again innovation, there are two types of innovation. One is incremental, another is disruptive. We look for disruptive innovation. Disruptive in the sense they should change the whole field altogether. With the invent of a cell phone, we know what happened to all our landline phones. So similarly, isn't it, many disruptive innovation can happen. It happens every day it happens. So now it's very challenging. Doing a research work is a very challenging one. Whatever you learn today, tomorrow it becomes obsolete. So you have to update every day. Our period was totally different. Whatever we learned, it was with us for quite a long time, 10 years, 20 years, something like this. No, people used to say that the half-life of any new technology is 2 years. You know the meaning of half-life, isn't it? All the chemistry students would be knowing that. That means whatever you learn, 50% would outdated within 2 years. So just I'm giving you the importance of learning every day, updating our knowledge every day. So that's with this idea in mind only, the Center for Research is organizing a lot of programs. It's just motivating you. This is not the end of it. You have to follow it quite sincerely. And of course, there are many facilities available provided by the university in terms of faculty, your peer group, and of course in the Center for Research, library, computing facility, laboratory, many things are available. It's up to you to make your subject and come out as successful. Okay, this introduction, now I want to come to my subject, that is the statistical inferences. So the statistical inference is different from mathematical inference. So mathematically, if somebody says that what is the difference between 40 and 40.01, people will immediately say that it's different. Mathematically, it's different. 40.01 is different from 40. But in terms of statistics, actually, when you have, I will explain what is this sample mean and all. When you have two sample means, one is 40, another is 45. One sample mean is 40, another sample mean is 45. Mathematically, 40 and 45 are different. But statistically is different. We cannot say immediately. We have to carry out a test, and finally only we can say that 40 and 45 may be statistically different or may not be different also. So that's why the statistical inference is different from mathematical inference, and there are a lot of fundamentals involved in making the correct inference from the statistical data. And most of you might have studied the statistics as a subject in UG or PG level. And you may be also wondering how a textile technology is talking about statistics. And you can also talk about statistics because it's application. When I was doing my PhD, I used statistics quite extensively. I learned. And as a student of MTech in IIT Delhi, I learned the subject, also one of the subjects in MTech program, offered by the mathematics department. So with that base in MTech and with application in PhD, and of course We introduced a new subject in our department. I was handling the subject for quite a long time. Now other faculty members are handling the subject. I could develop some knowledge in the field of statistics. So it requires both fundamental and application. If you are not fundamentally strong, you cannot apply it properly. Actually, it will misfire. So whatever the conclusion, inference you make, it need not be correct. So there are a lot of software available. SPSS, isn't it? R program, so many softwares are available now. You can feed the data, get the result, and somehow you can interpret and go. But understanding the basic concepts involved and the results, what the results exactly mean, whether it is relevant, whether it is repetitive, whether it is reproducible, all depends upon the knowledge you have. Otherwise, you can apply and get the results and publish it and go. But for useful application, the fundamental knowledge is important. So again, before I start any of my lecture, I used to give the important references required. These are the references I follow. It's not necessary that you have to follow these references. There are many references available. It's only indicative. So to understand what is statistics exactly, you should know about the concept of deterministic phenomenon and the probabilistic phenomenon. In the case of deterministic phenomenon, you can read that, isn't it, under identical condition, if you repeat the experiment, you will get the same result. So the example is, of course, from chemistry only you can give the example, classical example for deterministic phenomenon, the molecular weight, if you measure anywhere, anytime, you will get the same value, whether it is for carbon, oxygen, or any other element. And similarly, I used to give another example during the titration, isn't it? When we titrate, so what the value you take, isn't it? The concurrent value only you will take. First time, second time, third time, whatever it is, isn't it? If the repeated values are same, concurrent, that value only we take. Is because there is only unique value. The unique value only give the titrated volume. That is deterministic. There is only one value. It's not the average of the number of titration we have done, isn't it? We will not take the average of the volumes. It's the concurrent value. It means that there is only one unique value. The volume of what is available in the burette can react with the volume of the liquid that is available in the beaker. Unique, one value. It's not average. So that's the example of the deterministic phenomenon. And in the case of a probabilistic phenomenon, there are many examples actually. Most of the phenomena are probabilistic. If you measure under identical condition and if you repeat, you may not get the same value. If you measure the strength of a material, isn't it? Iron material, in my case, is a yarn, isn't it? If you repeat, you will not get the same value. There are many values. What we will do, we will take the average, standard deviation, or something like this. So basically, two types of phenomena. One is deterministic, another is probabilistic. The statistics is involved with the probabilistic phenomena, and the variable involved with the probabilistic phenomena is the random variable. All of you know that. So the random variable is a variable. Variable means it will keep on changing, definitely. It's not a constant. Random means we don't know what would be the value of the random variable. We cannot predict. We cannot predict the value of the random variable. So if you take, of course, here it is a controlled environment. If you go outside, if you measure the temperature now, and at 10 o'clock, what will be the temperature, we cannot predict. It's very difficult. Many parameters would influence the temperature outside, isn't it? So that means the random variable. So the characteristic of the random variable is its value cannot be predicted in advance. If it is a closed environment, isn't it? Of course, if you do some experimentation, if you change the volume, you can predict the pressure, you can predict the temperature in a closed, controlled environment. That may become the deterministic. But outside, it is totally uncontrollable. So the change in temperature would be unpredictable. So that comes under probabilistic phenomena. So at the bottom, I have given one important pattern. So that is the the value of the random variable cannot be predicted, but its frequency of occurrence against the value of the random variable, if you plot, you will get a stable pattern. Stable means it will remain stable. And it will be stable only if you make a large number of observations, very large number of observations. Large means you can take it to 1 billion or 1 trillion or something like this, theoretically speaking. Large number of observations if you make, you will get the stable pattern. It means again that if you get the diagram from small number of observations, 30, 40, 50, the pattern will not be stable. The pattern will not be stable. That's the most important fundamental point associated with the probability theory. That is, the frequency against value of the random variable will be stable over a large number of observations. From this pattern, stable pattern only, we can make all the prediction, we can understand the behavior of the random variable. If the pattern is not stable, I would say that the whole subject of statistics would not have evolved. I will not be here to talk about statistics. Fortunately or unfortunately, we are able to get a stable pattern that allows us to systematically analyze the behavior of the random variable. So it's simple. Whatever I told so far can be simplified with the two statements. If it is a deterministic variable, it can be explained by a single value. Single value is sufficient. So the atomic number of a carbon, isn't it? Atomic number of a carbon is 6, if I am correct, isn't it? 6. The single value is sufficient to explain that. If it is a probabilistic variable, single value is not sufficient. As I told you that if you make a repeated measurement, you will not get the same value. If you get the same value as in the deterministic variable, then single value is sufficient. But in the case of probabilistic variable, if you repeat, you will get different values and it will have a distribution. As I shown you in the previous graph, isn't it there? So we require a full distribution diagram to explain the behavior of the random variable. You understand the difference, fundamental difference between the deterministic phenomenon and the probabilistic phenomenon. So the deterministic variable, one value is sufficient to explain that. But in the case of probabilistic variable, you require a distribution. You require a distribution. Without having the distribution, it's not possible to understand the behavior of the random variable. And of course, we have many standard distribution. All of you might be aware, the binomial distribution and the Poisson distribution, and more commonly, the normal distribution. So it's a more common distribution we apply in most of the cases. So I given the probability density function of the normal distribution, and at the bottom there are different shapes of the normal distribution that depends upon the mean value and the standard deviation. Mean value is mu, standard deviation is sigma. So a normal distribution will have two parameters, and the two parameters is one is mean mu and the other is standard deviation sigma. Every random variable will have its own mu, own sigma. Every random variable, if it follows normal distribution, it can have its own mu and own sigma. It will be different. Depending upon the value mu and sigma, the distribution would be like this. I given some example for the varying mu and sigma, the shape of the distribution. It can be wide, it can be narrow, isn't it? Depending upon the sigma value and the mu value. So again I repeat, every population requires a distribution, and the distribution will have some parameters. The main purpose of the statistics is to evaluate the value of the parameter. So once you know the parameter, values of the parameter, you can totally understand the behavior of the random variable, as I said that, isn't it? Every random variable requires a distribution to understand its behavior. The distribution has some parameter. Once you know the parameter, then only you can totally define the distribution. So what's the main job of our research work most of the time would be to find out the value of the parameter, either mu or sigma, or if you use some other distribution, there are variable distribution, there are exponential distribution, geometric distribution. So every distribution will have its own parameter. We will try to find out the parameter, value of the parameter, whatever the variable we study. Random variable behavior will be different, isn't it? It may be geology in one way, in chemical engineering it may be another way, isn't it? Civil engineering can be totally a different, the behavior of the random variable we may be studying. Accordingly, you have to choose the correct distribution. As I said that there are many standard distributions, you have to select the correct distribution and find out the parameter associated with that. But normally what happens, it's not possible to test the whole population. I said that initially itself I have given a very large number, million, billion, trillion or something. The population will have so many data. So when you have so many data, we cannot test each and every element of the population. It's not possible. So what normally we do, you may be aware that, and what we do in all our research work also, we take a sample. And from the sample, we do the estimation of the parameter. Sample, and there is a big population. Population is very big, and the sample is very small. From the small sample, we estimate the parameters of the population. So in the estimation, we have basically three different types. One is the point, another is the interval, the third is the hypothesis testing. And point estimation is a single value that will be attached to the population parameter. An example, when you take a sample, we measure the sample mean and we say that this is the estimate of the population mean. This is normally we do. There may be million of data in the population. What we do, we take 30 or 40 or 50 specimen from the population, find the mean, and of course this sample is random sample. Random means it will represent the whole population. It's not bias. There's a difference between bias sampling and random sampling. Random sampling means it should totally represent. It's not from a particular region or particular time or something like this. It will represent the whole population. So the mean of the random sample, we can assume that it will be the estimate of the population mean. And similarly, if you want to measure the standard deviation or the variance for that matter, you all know that the square of the standard deviation is the variance. I assume so many things, but whenever it is necessary, I will give you also the explanation. So the population variance, the estimator is something like S square, and I given the formula. I need not go into the details of the formula. I will try to explain the concepts involved in arriving at all these solutions. Of course, there are many textbooks available. You can refer that. I will try to complement, isn't it, the explanation given in the most of the textbooks. I will try to give extra information so that when you read the textbook, you may understand quite easily. That's the purpose of my lecture. It's not reproducing what is available in the textbook. I will complement. I will give something extra to make you understand easily the concept. And instead of giving a single value for the population mean, we will explain them in terms of some interval between this value and that value. So there are some confidence limits or interval we call. So when I say that the confidence interval is the sample mean plus or minus L. The L value, how it can be calculated, I given in the bottom. The second and third line I given. So when you attach some range, so that means the population mean will lie between this lower value to the higher value. There is a range given. So now we are more confident, and instead of single value, we are giving a range that will be more confident, in the sense we will attach a confidence level also. 95% confidence level or 99% confidence level, we will attach to that and say that the population mean will lie between this and that. So this is another way of estimating the population parameter. Again, I repeat, our now objective of our discussion is to find out the value of the population parameter, because every population would have a distribution, and the distribution will have the parameter, isn't it? So that parameter we want to estimate. So far I told you about how we can estimate from the point of view of point estimation. The next is the interval estimation. Of course, this is another important information all the research scholars would be interested to know. So when we carry out a test, how many tests we should do? How many tests? So a single test, or 2 or 3 or 10 or 30, isn't it? So how do we limit? We should not limit depending upon the constraint available in the laboratory, isn't it? It should not be based on the constraint, the time available or the budget available. It should not be like that. It should be based on certain statistical basis. I given the formula. The n is the sample size. It should be equal to Z alpha by 2. I will explain what is Z alpha by 2. Into CV percent square, you know that the CV percent of the variable what we are studying, divided by the error percentage we can include, error percentage square, that we can include. Understand? The Z alpha by 2 is in the distribution diagram. I mark here. Isn't it? Yes, that is Z alpha by 2. In a normal, standard normal distribution diagram, from the table you can arrive at the Z alpha by 2. Or 95% level or 99% level or 90% level you can arrive. Okay, just one thing from the table. The other two parameters are very important. That is the CV percent of the variable what you are studying, divided by the error percentage square, but how much error you can allow. So this is the decision should be taken by the research scholar. The statistician will not give any solution. They cannot give. You ask any statistician, he cannot say that you limit it to 1%, 2%. No. It depends upon the situation where you are. Sometimes you may allow 1% error. Sometimes even 0.1% error also you cannot allow. If you allow 0.1%, things should go haywire. You cannot control it, and that may not be useful. That would have some devastating effect on the response. So you cannot do that. So sometimes the consequence may be very light. You can allow 10% error. Nothing will happen. Understand? So selecting the error percentage depends upon the situation, depends upon the variable you are studying. Sometimes it may be very sensitive, sometimes it may be less sensitive. So I would give an example that when we design a satellite or a spacecraft, we cannot allow large error. Isn't it? Large error, then you can understand what will happen. Isn't it? But sometimes in the other cases, particularly I am from textiles, I would say that in a textile garment, isn't that if the error is on the higher side, nothing much serious consequence would happen. Isn't it? You imagine what will happen if error is there in a flying spacecraft. Isn't it? So what will happen isn't it? That's the shirt I'm just wearing. If it fails, what will happen? If it fails, it means some kind of embarrassment. That's all to me. May not be to you, isn't it? Some embarrassment. That's all. Isn't it? That is manageable. But in the spacecraft, isn't it? No, we cannot allow. So that's why I'm repeating and re-emphasizing the importance of the selection of E square in your calculation. Don't take the textbook, they may have given many examples, 1%, 2%, not like that. You have to arrive at your own E person. So that is the discretion, isn't it? Depends on you. Your discretion will play a major role in arriving at the correct sample size and the interpretation of the results after that. It's clear. And of course, CV person is the CV person of the variable you are studying. It can be measured. It can be measured, and you apply that correct CV person, and you will get the correct sample size. So all the research scholars, isn't it? Before you carry out any test, how many tests you should do should be based on this basis. So I used to interact with the industry people also. So when I talk to the industry people, I will give the formula and stop. But being a research scholar, you should understand the implication of this estimation. So the sample mean, you please understand the sample mean is I told the estimation of the population mean. The sample mean is the estimation of the, you can listen to me. The sample mean is the estimation of the population mean. And there's a difference. The sample mean will not be equal to population mean, definitely, isn't it? Because it's a small size, that is the population is a big one. There would be a difference. The difference between sample mean and there would be a difference between the sample mean and the population mean. And the difference, we call it as sampling error. The difference between the population mean and the sample mean, we call it as the sampling error. So every estimation would suffer from this error, the sampling error, every estimation. So I put a question to you, let's see who can answer the correct one. If the sampling error has to be zero, what should be the sample size? Whole population, isn't it? If the sample size is whole population, then the sampling error would be zero. So normally it will not, isn't it? Cannot. Particularly in the research, isn't it? We will be limited to some number of specimens. So it will suffer from sampling error. You should be aware of that. And the sample mean, what we calculate, is not a constant. It's not a constant. It's a random variable. Population mean is a constant. Please remember, population mean is a constant. So we estimate the population mean from a sample mean, which is a random variable. It keep on changing. If you take another sample, you will get another sample mean. Third means third sample mean, isn't it? You have to understand. Because as a research scholar, you should not think that whatever the mean value obtained is constant and it is exactly equal to the population mean. No way. So some limited number, 4 or 5 tests, we will make conclusion on that. Isn't it? You have to make a conclusion, but when we make conclusion, be conscious, please remember that isn't it, the estimation is variable and it will suffer from some error, sampling error. It's not equal to the population mean. So again I told that there is an error involved in the estimation and the maximum error would be E%, isn't it? So we can select that maximum error, accordingly you can calculate the sample mean. The maximum error will be limited not all the time. Not all the time, isn't it? From the graph you would notice that it's not 100% confidence, it's not 100%, some 90% or 95 or 99%, isn't it? The rest of the time, the error can be more than E%. The error can be more than E%. So we calculate the sample size based on the maximum error we can allow. Again, that maximum error will be limited to 100 minus alpha percentage only. Remaining alpha percentage of times, isn't it, the error can be more than that. So be conscious about that. That's a point I want to convey here. And the remaining alpha percent, I just mentioned that it would be more than E%. And above all, so when we have a sample mean, we exactly don't know whether the error is within E% or more than E%. Understand? We have a sample mean, we calculate the sample mean based on the formula, isn't it, n equal to all those things, limiting the error to E%. But in the given sample, whether the error would be less than E% or more than E%, nobody can say that. But what we can say that when we calculate the sample mean, if it is 90% confidence level, 90% of the time the error will be limited to E%. That's all we can say. Whether the particular occasion it is limited or not, we cannot say that. I think I'm not adding confusion. I think this is a reality. This is a reality. As a research scholar, you should know that. Definitely we know that. Whether others are aware or not, we should be aware. And I'm giving another formula. This is the testing the hypothesis. So what is the difference? In the first formula I gave, we don't know anything about the population mean. So if we want to estimate the population mean, I apply the formula like that. In testing the hypothesis, I want to make a decision. I want to make there, in the first case, I'm open. I'm not very particular about any specific value for the population mean. I'm not particular. Just I want to know what would be the population mean. Here in testing the hypothesis, I'm specific. I want to make a decision that the population mean should be equal to mu1. I say that. And it should not be equal to mu2. Now I am specific. It should be mu1 and it should not be mu2. So in that case, if you want to estimate the population mean, this is the formula. Here the mu1 and mu2 are involved because you are specific. The other case, you are not specific. General E%. Here in the denominator, you have mu1 and mu2. This is one you want and one you don't want. So of course, I explained the hypothesis testing in the form of the normal distribution diagram. The left hand side is the population we want, and the right hand side isn't it the population we don't require. So the alpha is significance level or the type 1 error, and I have marked beta. The other side you could the hatch region is beta. The cross region is beta. The hatch region is alpha. So alpha is type 1 error. Beta is type 2 error. So when testing the hypothesis, you all know that there is null hypothesis and the next is alternative hypothesis. So we will take a decision either to accept the null hypothesis or reject the null hypothesis. One of the decisions we have to take, isn't it? When we accept the null hypothesis, it means that we reject the alternative hypothesis, isn't it? So one of the decisions we have to make. In either case, we will commit an error. Either case. Either you accept or reject the null hypothesis, you will make an error. So when we reject the null hypothesis, when it is true, when you reject the null hypothesis, when it is true, so the error is alpha. Because isn't it alpha is the critical region, alpha rejection region. So we will reject the null hypothesis, and probably it may be the correct one. We take a sample again. Some more explanation if I want to give it to you. All estimations are based on the sample. So I take a sample, I find out the mean, and from the mean value I have to take a decision whether the sample is from the population whose mean is mu1 or not. It's clear. I have to take a decision. I will explain in detail. I think that explanation is now looks to be important. That's why I will explain on this line. A sample mean, so assume that I want to test whether the population mean is 50 or not. The population mean is equal to 50 or not. That is my testing. But what I do is I take a sample of small size and find out the mean. The mean happens to be 48. The sample mean happens to be 48. So what decision I can take? You understand? The population mean I am looking for is 50. I have taken a sample from the population and its mean is 48. How can I take a decision? So this is a real classical example of statistical inference. If you have some answer, you give, otherwise I will move on. So, since it is 48 is smaller than 50, we cannot say that the population mean is not equal to 50. We cannot make that decision. That's the explanation I gave in the beginning itself. Statistical inference is different from mathematical inference. Mathematically, you can definitely say 48 is less than 50. But statistically, we cannot take a decision immediately. We require a statistic. We require a statistic. So that is I given as Z. So the null hypothesis equal to mu naught. In the example I given is 50. Mu equal to 50. The alternative hypothesis, I say that the mu is not equal to 50. How to conclude? To make a conclusion, we require a statistic. The definition of statistic is the information obtained from a sample. Information obtained from a sample is called as statistic. The subject is itself statistics, but they are given the name statistic for any information obtained from the sample. Any information obtained from the sample. So we require a statistic to take a decision whether the sample is from the population we require or not. Understand? So immediately on seeing the difference 48 and 50, we cannot make any decision. It's clear. So sample mean is 48, population mean what we want is 50. So there is a difference. Based on the difference, we cannot take any decision. We cannot take statistically any decision. Statistically, it's not possible to take any decision. This is a fundamental point I told you. So to take a decision, we require a statistic. Understand? We require a statistic, and statistics can be in many form. Statistic in the sense the factor. the factor obtained from the sample. The factor obtained from the sample is the statistic you require. Here I given an example of Z statistic. So what is Z statistic? You see that x bar minus mu naught divided by sigma by root n. This is the statistics we use to take a decision. X bar is the sample mean, we know that. Mu naught also the value, we know that. Divided by sigma is the standard deviation of the population. We should have that value. And of course, the n is the sample size we have used, sample size, number of tests we have carried out. So now we can get the Z. Once we know the Z, if it is a single tile, actually, we want to find out whether that Z value falls within the crossed area, that is the critical area, or within the normal area. So if it falls in the critical area, then we reject the null hypothesis. We reject the null hypothesis when it falls in the critical area. And that alpha, I told you, the type 1 error. The alpha is the type 1 error. That means we reject the null hypothesis when the value falls there. We reject. But there is a possibility that the sample might belong to the correct population. There is a possibility. What is the possibility? The possibility is alpha. The probability is alpha. So that's why we call it as the error, type 1 error. Type 1 error is nothing but rejecting the null hypothesis when it is true. And sometimes when it falls, so when it falls within the normal area, that means not in the hashed area. You forgot about the crossed area, not in the hashed area. If it falls within the normal area, we will accept the null hypothesis, isn't it? Again, when we accept the null hypothesis, when the value falls in the crossed area, that there is a possibility that it might belong to another population, mu2. Are you able to follow me? So that there is a possibility is beta. I marked that in the diagram, and the beta is the type 2 error. So either you accept or reject, you will commit an error. So that error is called type 1 error, alpha, type 2 error, beta. Rejecting the null hypothesis when it is true is alpha, isn't it? And accepting the null hypothesis when it is false is beta. So again, now I want to make an appeal to all the research scholars that the selection of alpha and beta cannot be arbitrary, isn't it? As I said that in the selection of E person, our knowledge, our understanding plays a role in selecting the E person. Similarly, so what do you do actually when you compare two results, isn't it? So you conduct an experiment with one particular level of a variable and produce a product, and conduct another experiment, isn't it, at different level and make a product. So what will you do? You take sample 1, sample 2, isn't it, compare the mean and take the decision, isn't it? You will take the decision. What decision? Isn't it the two samples are from two different populations or they are same? That means whatever the changes we made in the experimentation, has it produced any result or not? Most of the time we will be doing that. Most of the time the research scholars will be making some changes in the experimentation. They will do some changes in the experimentation and want to know that whether the changes that made any remarkable or significant difference in the final output. That's our main objective, isn't it? When you do that, we are not testing the whole population. Please remember, we are not testing the whole population. We will take sample 1, sample 2, compare and take decision. And when you take decision, I repeat, there would be error. So that error is in the form of alpha and beta. And you have to select the level of alpha. Most of the time while doing the subject statistics, So we will assume alpha equal to 0.05, something like this, most of the time. But that is for the textbook, solving the textbook problem. To solve the real problem, again I make an appeal. Please understand that what would be the consequence? What would be the consequence when you reject a null hypothesis when it is true? What would be the consequence? If the consequence is severe, alpha should be lower. Isn't it? The error, alpha is the error. What is the error? Rejecting the null hypothesis when it is true. The consequences will not be same in all the cases. Here there may be some 50 or 60 research scholars when they are doing their work. The consequence of any experimentation is that it will not be the same. In some cases, you can keep alpha of 0.1, and another case it cannot be 0.01 would be the appropriate one. 0.01 or 0.1. Who can decide? No answer in the textbook, I would say that. No answer. Only the research scholar has to arrive. Based on the knowledge he has, isn't what consequence it will have. Severe consequence, you have to limit the alpha to a lower level. Nothing to worry about that, not much consequence, then you can keep it at the higher level. Even in the industry, while as I told you that I interact with the industry, in the industry it is very important. Isn't it? For us, we may not face the consequences immediately, nobody will question you. Isn't it? When you keep alpha higher or lower, isn't it? Nobody is there to pull up your collar and question you. No such situation as a research scholar. But the industry, when they keep alpha higher, when it has to be lower, isn't it? They have to face the consequences. So they will be very sensitive. But as a research scholar, also, you have to be very sensitive and arrive at the correct value of alpha and beta. Again, I appeal to you, isn't it, when you do that experimentation with the correct input, whatever the results you will have, it will be useful to the society. Again, finally, that's the main point we have to consider. So this is the thing, as I already told you, the alpha is having another name, that is the producer risk. In terms of the industry point of view, is a producer risk. Actually, it is a risk. You can imagine if you are in the position of a producer, isn't it? You will be very careful because it's a risk involved, cost involved. And similarly, beta is a consumer risk. As a consumer, isn't it? What would be the risk? So, the testing the hypothesis goes on in many ways actually, isn't it? A single tail, two tail, testing a single population, testing a two population, and testing the means of the population, testing the variance of the population. So accordingly, isn't it, depending upon the situation, the statistics varies. Here the statistics is Z. Here the statistics is T distribution, all of you know that. When we don't know the value of sigma, in the other case there is sigma, the denominator there is a sigma. When the value of sigma is not known, we have to go for the T distribution, the T statistic, and it involves S. S is the estimation of the population standard deviation, as I already told you. And this is when we want to test the proportion, how many defects are present in a consignment, proportion of defects. So when you test the proportion, this is the statistics you have to use. And again, not only mean, you can test the variances. So whether the population has this variance, the null hypothesis is sigma square equal to sigma naught square. Sigma naught square is a specific value, whether the variance is 15 or not. If you want to study, you have to use the chi-square distribution. and chi-square is a statistic. So the selection of statistic, it depends upon the type of test you carry out. Whether we compare means, compare variance of single population or two population. So depending upon that, the statistic, here the chi-square is the statistic. And again, this is when testing the two population, this is the Z. And again, there are conditions, as I told you, it goes on in many ways. So when the sigma 1 square equal to sigma 2 square, and this is a statistic, T is the statistic, and when it is not equal, the statistic is different, the calculation of the statistic is different. And this is for the difference between the means of two population, difference between the mean, D is the difference between. And again the proportion from the two population. And of course, this is the decision we want to make about the variances of two population, We have a population, two population, so one population value is assumed that it is sigma 1 square, another population is sigma 2 square, the variances. And we want to see whether the variances are same or different. Sigma 1 square is equal to sigma 2 square or they are different. So what normally we do, as I said, that we take a sample. From the sample we calculate the sample standard deviation, S square. S1 square in this case, S2 square. So the ratio follows the F distribution. So Z distribution, T distribution, chi-square distribution, here the F distribution. So this F distribution, isn't it, we calculate the statistic. Again, when we want to take the decision, isn't it the same thing? Isn't it, we have to go back to the distribution diagram. The distribution diagram will have, isn't it, the critical region and non-critical region. If the value falls in the critical region, we reject the null hypothesis. When it falls, isn't it, in the non-critical region, we accept the null hypothesis. That's the way. The way is same. So far, I told you about what is the statistical inference, isn't it? The statistical inference, I would put a question, whatever I told you. So the statistical inference is made based on, so mathematics, pardon? What is required? What is required to take a statistical inference or statistical decision? We require a statistic. This is the point I told you, isn't it? Mathematical inference is easy, you can compare and take a decision immediately within the two value. But here, isn't it, in statistics, we have two values, sample mean, population mean, sample variance, population variance. Comparing the two value, we cannot take decision. We cannot take decision comparing these two value. Not possible, isn't it? So what we require? We require a statistic. So please, this is a point I wanted to convey to you so far. We require a statistic. And the statistic can be in the form of Z, T, chi-square or F. Isn't it? So you have to calculate a statistic. And this statistic, the calculated value should be compared with the table. And take the decision. So basis is this, isn't it? When you want to make a statistical decision or statistical inference, you require a statistic. So thus I explained so far many situations, isn't it? Two population, single population, variance known, variance not known, variance equal or not equal, isn't it? Accordingly, the calculation of the statistics will be different. The calculation of the statistic will be different. And once you calculated the statistic, either T, Z, F or chi-square, isn't it? You have to compare with the corresponding table value. You have to compare it with the corresponding table value, isn't it? or in the form of a distribution diagram. In the form of a distribution diagram, I told you, is if the value falls in the critical region, we reject the hypothesis, and it falls in the non-critical region, we accept the null hypothesis. This is the basis. This is a basis. So hoping that you understood the basis of the statistical inference. I have another 20 minutes time. I will try to explain about the analysis of variance. Like testing the hypothesis, most of the time, isn't it, all the research scholars will be doing analysis of variance in one form or other. So those who are dealing with experimentation, particularly those who are theoretical work may not be required, those who are doing experimentation, so definitely would be the analysis of variance would be involved in taking a decision. As I said that when you make a change in the process or in the product design, will it have any real improvement or not, isn't it? To take a decision, you have to apply this kind of testing the hypothesis and the analysis of variance. Here the analysis of variance, actually I would say that this is the most interesting topic in statistics. And a long time back, isn't it, the scientist Fisher used the concept to arrive at the conclusion on the agricultural yield. So he started applying this statistics or the analysis of variance, simply called as ANOVA, to know about the yield per acre from the different conditions. Isn't it? Agriculture, isn't it, first industry, isn't it, people develop. Later on, of course, now we come to tech industry. So in the agriculture industry, in the agriculture area, isn't it, people would be very much interested to know about the yield. They have plot, they will, isn't it, sow it, and they will find out, isn't it, and under different condition. As I said, that the experimental condition may be different. One fertilizer, another fertilizer, or the irrigation level, or so many things, they will change the experimental variable, isn't it, and find out and get the product, isn't it, and the yield. And they want to know whether is there any significant difference in the yield from the different plots. So they want to know, isn't it, if one experimental condition gives a better product, definitely they can make use of that, they can improve upon that. Isn't it? This is the way the application of the statistics started a long back. And of course, in doing the analysis, the fundamental model of a variable, say the yield is y, yield or the response. We can give a different name, yield or the response, y. Y is the response. The response is equal to inverse or mean, a common mean, plus tau I plus epsilon ij. So they are getting a yield. So the yield we can partition into three components. One is a common mean. So there's a constant. Common mean is the constant. To the common mean is added the other two factors. One is the effect of the treatment. Effect of the treatment would add or get subtracted from the mean, isn't it? Understand? Yij is the output. The output is equal to a common mean, and the common mean is affected by two ways. One is the treatment, another is the epsilon and the error. I will come to the error later. So So if you know about the treatment can add value to the mu, isn't it? Or there can be a subtraction, isn't it? Either the treatment could increase the yield or decrease the yield, isn't it? Naturally would be there or no effect. So there are three possibilities, isn't it? Whatever the treatment we make, whatever the treatment means, whatever the changes we make, isn't it? This we will be doing in all the cases, in all the experimentation, all the research scholars in all the experimentation would be making some change. So the change you make, I call it a treatment. So that treatment would affect the common mean, one way or other, increase or decrease. Okay. Added to that is epsilon ij or epsilon. You don't worry about the suffixes. The epsilon is the random error. So that epsilon is caused by unknown and uncontrollable factors. Unknown and uncontrollable factors. So we cannot do anything on that because it is unknown and uncontrollable. It will be there always. And statistically, this epsilon follows a normal distribution. Epsilon is an assumption. Epsilon follows normal distribution with mean 0 and variance sigma square. Mean 0 and variance sigma square. So what would be our aim? Whether this treatment has influenced our yield or not. We have to find out. So it can be found out again. We require a statistic. I told you the statistic what we use is F, and F is, you see here, ST square divided by SC square. So what is ST squared? Is the variance caused by the treatment, and SC squared is the variance due to the random error, isn't it? You see the equation, you see the equation, isn't it? The mean value, which is a constant, could be affected by two factors. One is the treatment you make, another is the error. Error is automatically happening because you don't have any control over that, isn't it? Unknown, uncontrollable. These two can affect your yield. Now we want to take a decision. What decision we want to take? Whether the treatment has made any significant effect or contribution to the output. It's clear, isn't it? This we are interested, isn't it? All the research scholars would be interested. Isn't it? Whatever the changes you made in the experimentation, has it made any improvement in the process or the product? You want to know that, isn't it? So that variation is nothing but ST square, isn't it? The variation caused by the treatment. We can calculate. I'm not going into the calculation part, but understand the theory, isn't it? So the response is equal to one common mean plus the treatment effect plus the error effect. So what we calculate, the variance caused by the treatment. Variance caused by the treatment. And of course the variance caused by the error. So error also causes some variation, isn't it? So this variance we calculate and take it as a F statistic. F statistic is ST squared divided by SC squared. Now you tell me that, isn't it? In which case you would say that whatever the changes you made, the treatment has got some significant effect on the product. When the value of F is so again I explain. Isn't it? So there are two causes for variation in the yield. There are two causes, isn't it, for the variation in the effect. Effect is Y, isn't it? One is due to treatment, another is due to error. You compare the treatment variance with the error variance. So when you say that the treatment has got a significant effect on your response, when you say that, when isn't it the treatment of variance is more, isn't it? When the treatment variance is more in the sense it should be comparably more than the variance caused by the error, isn't it? Not only more, it should be sufficiently larger than the variance caused by the error. If both are equal, isn't it, then we cannot say that the treatment has got any effect. Isn't it? It's almost equal to the variance caused by the error, isn't it? So no greater improvement we could expect from the treatment. So this is the way we conclude, isn't it, whether the treatment has got any effect. Of course, when the F value is greater than 1, immediately we won't take conclusion, isn't it? We have to refer the table. This is F calculation, there is F table, isn't it? If it is in the critical region, we reject the null hypothesis. When it is non-critical, we accept the null hypothesis. This is the general method we follow for taking a decision. But the method is same, but the selection of statistic is different. Selection of the statistic is only different. Isn't it? Here it is F. And the calculation of ST square, AC square, we can do that and make a decision. And when compared with the testing the hypothesis, the basic difference with the analysis of variances isn't that in the testing the hypothesis, I told you that we can compare two populations. We can compare two populations. Or otherwise, we can compare two levels of treatment. Treatment 1 or treatment 2. That's all. But here in the analysis of variance, there is no limit. You can have more number of treatments. Treatment 1, 2, 3, 4, something like this. And among the treatments, is there any effect or not, we can find out. That is the main strength of the analysis of variance. And fundamentally, if you see that, the analysis of variance compare the variance. The analysis of variance compare the variance. And finally, we take the decision on the mean only. We take the decision on the mean. Whether the population we compare 3, 4 or population we compare, the means are same or not. If the means are not same, it means that the treatment has made some effect on the population. That's why the means are different. So the difference in the means are evaluated from the variance caused by the treatment. Please understand, isn't it? So in testing the hypothesis, straight away you use the mean, sample mean, to arrive at the whether the population mean is same or different. But here, to arrive at the difference among the population mean, we use the variances. ST square is the variance of caused by the treatment, AC is error. And likewise, we can move on. Since the time is limited, you can have another effect. You can include the block. Beta is a block. So you can do it in a different block, or different machines, or different machine heads. One experiment isn't that whether it is limited to a particular plot here or different plots or different batches of raw material, isn't it? Raw material, the material is same, but it comes from different batches. So different batches means we call it as the different blocks. And if you carry out the experiment instead of one machine or 4 machines, every machine is a block. Or even in the same machine, there may be different heads. 2, 3, 4, 5 heads, isn't it? If you carry out the experiment in different 5 heads, then every head would become a block. So you have to account for the block. The accounting for the block, this partitioning of the variances now is increased. So the partitioning is, there is a common mean, the variance caused by the treatment and the variation caused by the block, of course, the epsilon. So you can find out the interaction also, interaction between the tau and the beta. I have given that tau I beta j, the interaction, interactive effects also we can find out. Overall, this is the partitioning of the total sum square. So you assume that there are 100 observations. Assume that there are 100 observations. You can have a mean, overall mean, and there is an individual observation. So there is a difference between the individual observation and overall mean. You square the difference. That becomes the sum of square total. So 100 observation, overall mean, and every value observation would be different from the total mean. So the difference you square it and add it, isn't it? That becomes the total sum of square. So this total sum of square is nothing but equal to the sum of square caused by the factor 1, factor 2, and the interaction between factor 1 and factor 2, of course, finally the error. So you can partition, and this is the ANOVA. The analysis of variance means the variance can be partitioned. So this is the limit. Actually, we cannot go beyond that. Actually, there are only one-way analysis, two-way analysis. All of you know that only we can go up to two-way, and the factor 1 effect, factor 2 effect, and the interaction between the two factors. Of course, the error would be there, and we have to calculate the f value, isn't it? If you want to find out the ST square, ST1 treatment 1 divided by ST square, whether is there any significant effect on the yield, and similarly factor 2, the variance caused by the factor 2 divided by ST square, you have to compare it with the error variance. Whatever the variance caused by the factors or interaction, isn't it, should be compared with the error variance. If it is significantly more than the error variance, then the factor has got effect on the yield. So this is the concept. Of course, there may not be no time limited to that. I will stop here. So, and the extension of analysis of variance is the design of experiments, isn't it? So I already given you a lecture on the design of experiments. So I prepared that. If you have got some time, we can cover that fundamentally. So I will. Yes. So this is the final result of any design of experiment. Again, the response, isn't it? Analyze the variance, I given partition the variance, but from the design of experiment, you can arrive at the equation for the response in terms of the process variables. It's an equation, isn't it? It's a polynomial equation. Particularly, it's a second order polynomial equation. So any design of experiment finally would provide you an equation for the response. Response means that this is the parameter you are interested to know. It may be a strength, or it may be a concentration, or it may be anything you are finally interested to know. That is a response. So that response is explained in terms of process variables and in terms of the equation, of course. So if you know the coefficients of the equation, you can predict what would be your response. You can predict. Since the analysis of variance the prediction is not possible. Only we can conclude whether the treatment you have made has got any effect on the response or not. Only you can do that, an analysis of variance. That's all. But here, design of experiments, of course, this will be also very, very essential for all the research scholars, because it helps in prediction. And of course, the prediction would be correct if you could reduce the error involved in the design of experiments. A lot of error involved. Actually, you have to minimize the error or avoid the error. So then only your prediction would be better. It will not come just like that. It's very difficult because you go for prediction, isn't it? You all know that now there is a weather prediction, isn't it? How accurate it is, isn't it? Earlier it was less accurate. Every day they are improving the accuracy, isn't it? So similarly, isn't it? More and more data would improve the accuracy of the prediction. And all research scholars are supposed to be the scientists, isn't it? They should come out with some formula for predicting the performance of the product or the process, isn't it? Everybody would be interested to predict what will happen in future, and then only they can prepare now what should be done later. So, isn't it, with the blinded eyes, isn't it, if you move on, we don't know where to go, isn't it? If you could predict, then you throw some light on, isn't it, what will happen? So, those who can predict are well placed, better placed, particularly, isn't it, in the industry. So, all the research scholars, please don't assume your role is limited to lab. So, you have to provide solution to the industry. And that should be your aim. Now, that is the thrust. You cannot escape also, isn't it? When we study, actually, nobody bothered about publication. Now, later they ask about publication. Then they ask about patent. Then, what is the use with the patent? How do you, did you commercialize? Likewise, now they want startup. Isn't it? How many startups you have? How successful your startup companies are, isn't it? So the thrust on the scholars now are different, and the responsibility also different. So just you can learn and be content with that is no longer is valid. You have to provide solution. You have to provide solution. The university expects, the whole country expects that you should provide solution to the real-time problems, not solution what's available in the textbook. So the real-time problem. So I could not proceed further. I stop here. If opportunity comes, I would have more interaction with you in the later time. Thank you for your patience listening. So I am, as mentioned in the beginning, I am professor of eminence. I am in the textile department. If you want to have any further interaction, you can meet me personally also. Thank you.
Thank you so much, Professor, for the wonderful session. Scholars, if you have any queries, you can interact with Professor. If you have any queries related to statistics, how to apply them in your research, if you have any queries, you can just come on.
Introductory level, isn't it? So there are, you have to go deeper into that. While doing the calculation and all, I have not covered the calculation part, isn't it? It is all, lot of calculation involved. If you are interested, you can, as I said that, you can come to me anytime. You can interact with me anytime. I am available in the Department of Textile Technology. Of course, a prayer appointment will help us, isn't it? We can avoid disappointment.
Okay, so you have any queries?
Any questions?
Okay, I think this you can apply in any fields. It's not restricted to only one particular field. Any experiments you can apply statistics, and you can just add more results to your experiments, right? Having only your own experiment and results. You can also add some statistical analysis and see how the trend is varying and all those stuff. Professor, I really enjoyed your session, Professor. Thank you. Thanks a lot. So on behalf of Center for Research and Anna University, I extend my sincere thanks to you, Professor, for the voluntary contribution. Thanks a lot, Professor.
Thank you all.
Yeah.